All right, so this is a video on the structure of the atom and how it kind of came to develop. So first thing we need to understand is that um, all matter has mass and volume. Matter is really defined as anything that has mass and volume. Now sometimes instead of saying volume, we say that something takes up space, but it really means the same thing. So we say that matter is anything that has mass and volume, or matter is anything that has mass and takes up space. And then we know that all matter is made up of atoms. And atoms are the tiniest or the smallest particle of matter that retains these properties. It's as small as it gets. You can take any material and break it down smaller, 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 smaller. And if it's an element, you ultimately get to just a single atom of that element. Now, with today's knowledge, we know that atoms are made up of subatomic particles, and you could break an atom into even smaller pieces. But at that point, it no longer retains those properties of being the element. Like if I took an atom of gold and broke it down into its protons, neutrons, and electrons, those protons are not like gold protons. I don't have gold electrons. They're just protons, neutrons, and electrons. They no longer retain those common properties, chemical, physical properties of being gold. Now, if we get into like the actual theory, like atomic theory, what the actual model of an atom looks like, it starts way back with Democritus. Exactly what year is a little bit sketchy, but it's somewhere in the 460 to 440 BCE area, and so this is like about 2,500 years ago. And while Democritus is the main guy that gets credit for this, he's not the only one that had this idea. And he said that atoms are made up of these super tiny, uncuttable particles. So he actually named them atoms because of the Greek word atomos, which means indivisible. So they called these particles atoms. They're uncuttable particles because of the Greek word atomos. And then he really believed that there was essentially 4 different types of atoms. There was earth, fire, water, and air. And that all things were made up of one or some combination of these 4 elements. Now we know now that there's not like a fire atom and a water atom. We know that that's not really accurate. But remember, this was 2,500 years ago. They obviously had a different amount of base knowledge, a different amount of technology available to them to study this. The other thing is, Democritus was a philosopher. He was not a scientist. He really didn't concern himself with proof. Proof was not important to him in the same way that we place importance on proof or evidence now. So his idea stands largely unchecked, unaltered for like 2,200 years until John Dalton comes around. Now, John Dalton is a scientist, so he is concerned with proof. He does experiments, and from those experiments he concludes that all matter is composed of atoms. Those atoms of each element are all the same as each other. So like an atom of gold is the same as every other atom of gold. He also includes that atoms of different elements are always different from each other. So like an atom of gold and an atom of silver are different than each other always. And then lastly, and this is another big contribution, was that atoms of different elements could join together to make up new substances, which he called compounds. If we looked at Dalton's model of the atom, it largely looked like this, just a solid uniform ball of stuff. You could think of it as like a tiny marble that is the same throughout, all one color, all perfectly spherical, with nothing different inside or outside, always identical. Solid ball stuff, no subatomic particles or anything like that. And now remember, he's still early 1800s, so he's still, 200 years ago. Again, still talking about limited knowledge, limited technology. So pretty good idea, but not quite right. Now, about 50 years, 70 years after Dalton, we have this guy, J.J. Thomson. J.J. Thomson, like it's J.J., it makes it nice. I can remember the plum pudding is a PP model. No one eats plum pudding anymore. So we would actually, in today's day, we'd probably call this model the chocolate chip cookie model. So he discovered that there are negatively charged particles called electrons. So he's working with this device here called a gas discharge tube or a cathode ray tube, and is essentially sending a beam of particles from one side of the tube to the other side of the tube. But while he's doing this, he's holding up a magnet near the beam, near the glass tube. And the beam of particles either bends toward the magnet or it bends away from the magnet. And from this, he concludes, using some pre-existing knowledge, he concludes that this beam of particles is actually made up of negatively charged particles. He concludes this because at this day and age, they know some information. They know that magnets can affect electrically charged particles and will attract them or repel them. And they know that opposite charges attract. They know that like charges repel each other. And they also know that the atom is neutral, meaning it does not have an overall charge. It's not negatively charged or positively charged as a whole. So this also means that since he discovered that this beam of particles is made up of negatively charged particles, there must also be positively charged particles. So his model looks like this here, kind of like a chocolate chip cookie. You got this mound of positive stuff with little negative tiny pieces mixed into it. At the time, again, they called it plum pudding, the plum pudding model, but probably wouldn't go over too well nowadays if they called it the plum pudding model. So the chocolate chip cookie model, I think, would probably be our current name for it. Now, 20 or 30 years after J.J. Thomson, a guy that had been working with him, kind of a disciple by the name of Ernest Rutherford, comes around and does some additional experiments. Now, his idea of the atom had changed some since J.J. Thomson. And his belief, initially, going before he did his experiments, his belief is that an atom is mostly empty space, and that the positive and negative parts are spread out, kind of evenly distributed within the atom itself. But that's not accurate. And his experiments, his hypothesis going into his experiments is not fully supported. And so he comes up with a new idea. His expectation going into his experiments was that from this device, particle accelerator, that he would be able to send beams of particles out to this gold foil. And because he believed that atoms were mostly empty space, he believed sending tiny particles, they should be able to get through that empty space. And most of the particles will come out straight ahead on the other side. Some might bend just a little bit due to collisions with the tiny particles within the foil, but most would go through unexpected. And that's this, or undeflected, unmanipulated. And this here, that's what he expected. And while most of the particles did that, there were some particles like this guy over here and this guy over here that did not do what he expected. Instead of passing through the gold foil, they bounced back at pretty sharp angles. With this, he concluded, knowing that the particles that he was sending out were positively charged particles, he called them alpha particles, knowing that they were positively charged particles, he concluded that they must have come in contact, or at least in proximity, come close to a dense, positively charged area within the gold foil. So he concluded that the positively charged stuff in an atom must be dense and located in the center of the atom, and he called this the nucleus. So Rutherford with a U up here discovered the nucleus with a U down here. So that was his major contribution. Now, a contemporary of Rutherford, another guy that was working kind of in the same general time, but armed with Rutherford's new finding, a guy by the name of Bohr comes up with this new model. So Niels Bohr, I've heard it pronounced both ways, either one works. So Niels Bohr comes up with this idea that yes, the atom is mostly empty space. Yes, there's a positively charged nucleus in the middle. But in addition to that, the electrons exist in these levels at predetermined distances away from the nucleus. And that the electrons travel in very specific orbits around the nucleus. A lot like the way that planets would orbit the sun. And we know that now that this isn't quite right, but his model is close enough that we frequently use it when we talk about the atom. But this is not what happens. The atoms don't actually orbit in this very predictable orbit. There is levels. Atoms do exist in levels, but not in this predictable fashion that Bohr had thought. So some of his information, the idea of atoms being, or electrons being in levels, was correct, but some of it was not correct. They don't orbit. Now there was another component to his idea, and that's that as electrons gained energy, they could move to levels that were further away from the nucleus, and that as electrons lost energy, they would move to levels that were closer to the nucleus. And this also seems to be true. So this was not the end of it, though. This is still 1913. We're still talking 100 years ago. So since then, what we've kind of come up with, what our existing model contains informationally, is that atoms have subatomic particles, protons, neutrons, and electrons, and that protons and neutrons are located in the nucleus, and that the protons are positively charged, and the neutrons have no charge. We also know that electrons move around the outside of the nucleus and that they have a negative charge. And we know that in an atom that is uncombined, meaning it has not joined with another atom to form a compound or anything, so it's a single atom alone, has an equal number of protons and electrons. And this causes the atom as a whole to be neutral, because for every positive charge, every proton it has a negative charge to cancel that out. So this causes atoms to be neutral. So this kind of is our basic level of like current knowledge to this point. But there is a few other things that are worth mentioning. So we know that the atoms do not move in definitive paths, but rather they're found in this probable area out here called the electron cloud. So if we were actually to draw the most current model, it would look something like this, where you'd have a light-colored area where atoms or electrons could be, but it's not real probable, there's a low probability. And then here is an area of higher probability for electrons, and then lower probability, and higher probability. And so this causes your level 1, level 2, and so on. We also know that each level has a maximum number of electrons that it's capable of holding. The first level can only hold 2 electrons. The second level is capable of holding a maximum of 8. The third level is where things get a little bit tricky. The third level and on. So there's actually, we know of atoms up to 7 energy levels. We're just only going to be concerned with the first 3 levels this year. But from level 3 and on, there's a different number of electrons maximum depending on whether this level is the outermost level or not. So for every level, the third level on, the energy level is considered full with 8 electrons. But if that energy level is not the outermost level, then it can have more electrons than that. So the third energy level is capable of holding 8 electrons maximum if it's the outermost level. But if there are more levels further out than the third level, if there's a 4th, 5th, 6th, 7th energy level, then the third level can actually hold as many as 18 electrons. Still needs to have at least 8, but it could hold a different number greater than that, up to 18. It could hold 13, it could hold 11, it could hold 16, but it could hold as many as 18 maximum. But only if it's not the outermost level. And then again, the same thing happens with levels 4, 5, 6, and 7, but the maximum number is not always 18. But for every energy level from level 2 on, the maximum number, if it's the outermost level, is going to be 8. Now, we also have names for these outermost energy levels, because clearly there's some importance here. And the outermost energy level is called the valence shell, or the valence level. And then the electrons that are located on this valence shell are referred to as valence electrons. The goal of the atom is always to fill the outermost shell. But atoms have to start filling the inner level before they can move to the next level. So the first level has to be filled before electrons can make their way to the second level. The second level has to be filled before electrons can start to fill in the third level. The third level has to be filled, meaning 8, before a fourth level can start to be filled, and so on. So we have to fill from the inside levels out. So that's really kind of what our base of knowledge is up to this point and how we got to be there. So this is going to be the first part of these notes on the development of the atomic structure, the history of the atomic structure. there is going to be a second video, so please make sure you do come back and check that out as well. Thank you, guys.